Hello everyone, myself Ganavi, studying in Sri Venkateshwara College of Engineering from the Department of Computer Science. Today I am here to explain about a paper overview of the theory of computational complexity. The purpose of this paper is to outline the theory of computational complexity, which has emerged as a comprehensive theory during the last decade. This theory is concerned with the quantitative aspects of computations, and it is central theme in the measuring of difficulties of computing functions. Our paper concentrates on the study of computational complexity, measures that defines the all computable functions, and makes no attempt to survey the whole fixed exhaustively, not to represent a material in historical order. Rather, it represents the basic concepts, results, and the techniques of computational complexity from a new point of view, from which the ideas are more easily understood and fit together as a coherent whole. Need of theory computational complexity. A valuable theory of computation must consider a quantitative aspects of computing. It must go beyond classifying functions as computable or non-computable. It need to develop a general theory studying computational complexity measures. Goal of this theory is to study the properties of computational complexity measures, to assign the complexity to each terminating computing, to reflect the aspects of real computing, and to contribute the computer science development. Progresses and significant progresses made in developing computational theory. Now it is essential part of theory computation. It will permeate the theoretical works in computer science. The objectives of this paper, it outlines the central concepts, results, and the techniques of computational complexity theory. It mainly focuses on the computable partial function. It is not an exhaustive survey nor in an historical order. The overview, computational complexity theory studies resources required for the computations. It is an essential part of the theory of computations. The motive is to understand the difficulty of computing functions and to develop the general theory studying computation complexity that measures the computational complexity. Complexity classes bounded by recursive functions, the uniform constructions of large complexity classes, the gap theorem, that is limitations on the constructions of larger classes. Diagonalization, it is a process of constructing new complexity classes. It breaks down the piece of diagonalization into simultaneous and parallelization. Naming complexity classes. In union theorem, union of recursive enumerable complexity classes as a complexity class. Size of algorithm, the formal definitions of size measures. It is an recursive relations between the size measured. It is an insufficient representations in recursive enumerable list. Definitions of computations. A computational complexity measure is an admissible enumeration of partial recursive functions. It is associated with the function is a function of each step counting functions. There are two conditions that must hold. Algorithm halts if step counting functions is defined, and the recursive functions is to be determined halting within m steps. Properties are the recursive relations between the functions are functions and the complexity does not exist. The recursive function can bound size of computable functions by complexity. All complexity measures are recursively related. Key takeaways. Complexity classes are defined by bounding computable functions. Complexity, it uses the recursive functions. The gap theorem shows that there are the orbital large gaps among the recursive functions containing no running times. Some complexity classes are recursively enumerable, which while others are not. Measured set of functions can be used to construct the recursive complexity bounds. Overview. This section explores the diagnostic process over complexity classes. It also expresses the complexity of this process in terms of simultation and parallel computation. Diagonalization process. In this process, it constructs functions not in C by diagonalizing over all the computable functions. The original process checks if n is greater than n and constructs a new machine to compute CR of n. The new process bounds the simulation steps used in computing of n. Diagonalization can be expressed in terms of simulation and parallel computations. Specific complexity measures like time-bounded computations can be analyzed using these techniques. The results that provide insights into complexity of diagonalizations and the relationship between the complexity classes. The simultaneous functions S and the set of P's P are crucial in analyzing the complexity and diagonalization. The limit conditions in theorem 13 that ensures the simultaneous time is negligible compared to the running time T. The results have implications for understanding the complexity of computable functions and the relationship between the complexity classes. One-type Turing machines, a set of sequences R is T of 1 that is acceptable by one-type Turing machine. If it is acceptable within the T1 of n operation, the class of T of 1 acceptable sets is donated by CT1. Simulations for one-tapped Turing machine. Simulations is simpler than for many tape machines. Simulations can be carried out within a constant time of machines simulated. This is achieved by keeping a copy of a description of M or M near the simulation area. Sections on complexity classes. Setting of simulations after T1 operations is more difficult than for many tape machines. Difficulties arises from running two independent computations on the same tape within one head. The solution to overcome this problem is to run the processors on different tracks and move one process to ensure the head position do not separate. Theorem 14. If conditions are met, then C1 is approximately equal to 1. The implications of theorem 14 is it provides the conditions for containment of complexity classes that are defined by one-tape Turing machines. It highlights the differences in complexity between one-tape and many-tape Turing machines. Uh, Key differences from many tape machines. Simulations is cheap, that is a constant time for one tape machines. It is expensive for many tape machines. Parallelism is expensive, that requires track management for one tape machines. While in case of many tape machines, it is free. L1 of compatibility of L1 tape ensures that efficient parallelism. The constant simulation cost reflects tape-bounded computation's efficiency. Theorem 15 conditions that ensures the negligible simulations time compared to L of 1. Comparisons to other models. Tape-bounded computations differs from time-bounded computations. That is like many tape and the one-tape machines. Space complexity is a primary concern, not the time complexity. Naming of complexity classes. Union theorem. Um, in theorem 16, we let f of I be the recursively enumerable set of recursive functions such that fi of n is less than fi of 1, fi plus 1 of n. Then there exists a recursive function t of n such that ct is equals to ui cir. Key features: simulations and parallelisms are not used to construct t of n. T of n is greater than fi of n for each I and almost all n. Definitions of size measures. A size measure S is a recursive mapping of integers and integers to the integers. S satisfies three axioms: fitness, recursive, and enumerability. Fitness: for each j, there exist finitely many indices I such that S of I is equals to j. In recursive, there exist recursive functions that gives the size of each algorithm. In enumerability, there exist recursive functions that gives the number of algorithms of each sizes. Properties of size measures. All the all size measures are recursively related to theorem 18. The size measures captures the notations of complexity of the algorithms that are described. Consequences of theorem 19. Here it exists a primitive recursive functions whose smallest primitive recursively schema is much larger than a general recursive algorithm. Here, the implications in the theorem 19. The size measures captures the economy of formalism for representing algorithms. Conditional transfers are useful for efficient representation, not just computations. History and development of computational complexity. Early developments. The recursive function theory provided the formalism for computational complexity. The electronic computing and the computer science emphasizes the need for the quantity theory of computing. Major results and theorems. Gap theorem. Uh, Second is about recursive vulnerability and complexity classes. Third is stimulations and parallelism results. Fourth is union theorem and naming theorem. And the fifth is size of machine results. Milestones. In 1960s, emergences of computational complexities as a research areas. In 1965, Hartmanis and Strerer's papers on computational complexity. And also in 1965, Comban's conferences papers on quality aspects of computing were conducted. Impact of this is the computational complexity has become a major area of research in computer science. It is influenced by recursive function theory, automata theory, and the formal language theory. Applications in algorithm designs, computational efficiency, and cryptography. Open problem and future directions. We develop a new computational complexity measures. We also investigate the relationship between the complexity classes and to apply the computational complexity to the particular problem. Thank you.